All right, and welcome everybody. I'm glad you're back, and this is part 11 of my series about the modulation or power control for the heavy lift drone. And I do want to try to create a unified control panel that would be in all of the different heavy lift drones, using some of the features of drones, mostly related to their ability to be autonomous, where they can help you to fly the drone. And we're looking at right now, I don't know how to say these words, a tough cone on Jeju Island. Now, Jeju Island is in Korea. A lot of the Netflix Korean dramas, I only watch the ones in English, but they're kind of nice. They're pleasant. They don't seem so harsh. And a lot of them involve going to Jeju Island, if I'm saying that right. I've never seen this in any of those dramas. I think this would be a great structure for a movie scene or a scene in a show, but maybe Korea won't let them do it. We can take just a pause and go to Google Earth. And on this Google Earth, we are at the top. You just have to think of the number of people down there who said, oh yeah, we should go up there and look around, and not really fully comprehending just how many steps there are. And this looks very steep. Yeah, there might be some people who would say, well, I'll sit right here and I like this view. You guys go ahead. Tell me what it's like up there once you get there. I think we're somewhere around right here on that Google Earth view. And there's more of the walkway that's available. You get higher in the air here. This is that tough cone. They call it a tough cone. And of course, when you're a hammer, everything is a nail. If this would not be a cool place to put that drone right there and take it off and fly up here and land on this tough cone. Here's those. I'm just looking at this thinking, I don't know if I could get up all these steps. You have to wonder, I don't know what's down that way. There's probably an emergency room down here somewhere. I bet they've come up here to get people. Anyway, South Korea. And on this part 11, we're finally going to do the calculations. I wanted to do calculations because I think this heavy lift drone in a military setting could save United States soldiers, could prevent them from being hurt or more seriously hurt or have not a good outcome. And, you know, I'm a realist. I understand the military might say, okay, but we don't want this. Or they might say, well, we have money, but we don't want to spend our money on this. What I don't want is someone to listen to what I'm talking about and say, that is such a great idea. We really should have an airplane that doesn't need a runway. What a great concept, except it's just impossible. And I might say, and how did you come to the conclusion that it's impossible? And they say, well, you don't have to. You can just tell by looking that it won't work. It's impossible. And what I wanted to do was, at least by math, there's good aeronautical, aerodynamic calculation programs, and say, well, before you say that this is impossible, what did the math say? And when I did the math says, yeah, you want to make this thing, go for it. I completely understand. A lot of stuff seems pretty reasonable based on math, and then you create it and reality kicks in and it actually can't be done. But I don't want someone to just simply dismiss everyone from thinking about this on the grounds that there's no need to consider it because it's impossible. And my math says it's not impossible. Be fun to land it here. Put it down here. My guess is I've never seen a Korean movie that featured this. I just can't believe that Korea probably said, no, you're not going to have shows here, and you're certainly not going to land a plane on it, and absolutely you're not going to land an American military experimental plane. But that would be cool. All right. Now we'll open up the CorelDRAW presentation file that we've been working with. Oh, I think I wanted to do one other thing. Let's see, we got to get out of Street View and take a look. This is Google Earth, which does give you the ability. Again, I apologize for the flying of this. Just isn't. I don't see a. Oh, there's the. I was going to think that's a runway. I'm not sure if that's a runway, but I don't see a hospital anywhere. But anyway, this says down in through here, you can see over here is the elevation. So this is sea level, so that's 18 feet. Up here is 433 feet. So, you know, that's interesting, but it doesn't have the type of elevations that we saw at Gunnison. Now, on to the real stuff. And now we're in the CorelDRAW presentation. This again is my conclusion, which I started with. And we've gone through some of the pages. We've done. I do want to remember to say this. Any physically real object does have the possibility that it could damage structures or hurt people. Any physically real object should be managed in a manner where the management of it is legally allowed and reasonable and safe. And my advice is, do not make any physically real item. Just don't make it as a physically real item if you cannot manage it in a manner that is legally allowed and reasonable and safe. Some of the other pages, these are the soldiers that got in trouble. This is what I want this drone to help with. This is the drone that we're talking about in these calculations. It's a DHC-2 flying plane with a addition to it of the parts that allow it to have complete and total VTOL capability, run by two of the more modern jet engines, the CTS 800. They're running they're running Parker Hannifin bent axis hydraulic pumps, and these bent axis hydraulic pumps are creating pressurized hydraulic fluid that is sent to Parker Hannifin bent axis hydraulic motors in the propeller supports, and the motor is directly connected to the propeller. So whatever RPM the motor is running at, that is the RPM that the propeller is running at. And so this is what we're talking about. We're going to do the calculations to show that this is a feasible plan. And I do want you to know that I'm glad you're here and you're invited. I invite you to be a subscriber to my YouTube channel. I think you would enjoy it. There's a lot of stuff there, and more is coming. I've shown you a sneak peek of the unified control panel, but I'm going to do more discussion about that. The unified control panel was shown in part 11. And this whole document is a downloadable page on my website, and I'll show you how to go get that. And here is the home page of my website, pistonrobot.com. I do have stuff where I talk about robots, and I have stuff where I talk about topics that are not about a robot. This is the engine. I'm going to do a set of videos on this. This is an engine that creates power and it doesn't make any noise. It's very important for robots and drones. Discussion's not about a piston robot. So again, on the home page, if you click on this page, this menu item, discussion's not about a piston robot, you can go down to a variety of things that I was talking about. One of them here is the heavy lift drone. There it is, flying in Gunnison, one version. And you can click on the heavy lift drone. And when you click on the heavy lift drone, you get to the heavy lift drone page. I like my robot feet. I think they're cool. And on this page, there's a place right here. If you click on this, it will download a 60 megabyte PDF file of what I'm talking about. Now, I will mention that the CorelDRAW PDF has 29 pages. It used to be that it had 28 pages because I left page 29 out. Page 29 is where I show how to get the drone from flying at 40 miles per hour to flying at 60 miles per hour. And for those of you who have downloaded this and you want to have that page, just download it again and delete the old one, and the new one has that page. And we do, okay, here is the drone with its propellers creating vertical thrust so it can go straight up. Here it is starting to tilt the wings forward. This is a pusher propeller. These are pulling propellers to get horizontal motion. And here the propellers have been brought to a fully horizontal thrust condition for fixed wing flying. And that's what we're going to be talking about. And I think, as we did in part 11, this is Gunnison, where he flew up this valley and then put it on vertical flight and flew all the way up to this little spot and landed it right here. Because this can be done with a VTOL airplane, and then he can take it vertically straight up and just fly away again. And so in order for us to do the calculations, we need to do calculations about three different situations. One situation is where you're on the ground with zero airspeed and zero altitude, or zero altitude above ground level. His altitude right here is 12,000 feet. But you're at a 0-0 condition and you make the drone go straight up in the air. Then you go up to a certain altitude, and at that altitude you add horizontal velocity to the drone so it begins to have a horizontal airspeed. If you get the drone up to 60 miles per hour of airspeed, then the lift from the wings is equal to the weight of the drone, and you don't need to have any more vertical thrust from the propellers. The third thing I wanted to calculate was getting the drone, once it's been changed from having zero horizontal airspeed into having 60 miles per hour of horizontal airspeed, I want to bring it up to 125 miles per hour of horizontal airspeed, because that's the most efficient flying speed for the drone with respect to fuel consumption versus miles traveled. And all of that involves changing the tilt of the propellers. And that is this image that I created. Here is that same flying machine. That's a pushing propeller. That's a pulling propeller. So that both of these can be mounted on the same mounting structure. And so that lets it go vertically straight up in the air. As you tilt these forward, this is 18 degrees of tilt. Some of your thrust is vertical thrust, but some of it is horizontal thrust. The real thrust is like this. But this thrust like this can be mathematically treated as a component of vertical thrust and a component of horizontal thrust. And then, of course, you can bring the propellers to their full tilted condition so that they are creating nothing but exclusively horizontal thrust. And these are the calculations that we're going to show, because These 3 flying events have to happen in order for this drone to be useful and reasonable. Some of the calculations will generate numbers that just come out of the calculation. There are places where you have to just put a number in because you have to, or you can't go anywhere. For example, how high in the air should you go before you attempt to do a transition from vertical flying and 0 horizontal airspeed to start giving yourself horizontal airspeed? I picked 500 feet. Other people might say, oh no, it should be 800 feet. I have a feeling when military pilots get their hands on this plane, they will work out what's the best. I'm just gonna guess it'll be lower, but I don't know. I'm just being safe. I don't want the people flying it to get hurt. I think you need some altitude, so if you goof up your transition, you have some altitude left to try to fix what you just did. The jet engines provide the prime mover. They convert fuel into rotary force. That rotary force turns the pumps. The pumps create hydraulic flow under pressure to turn the motors. So for each of your conditions, you need to have a hydraulic flow and hydraulic pressure for the motors, and you need to have a hydraulic flow and a hydraulic pressure for the for the pumps. The way the motors work, as you give more flow of hydraulic fluid to the motor turns faster. So hydraulic flow controls RPM. The torque that the motor can create is related to the pressure of the hydraulic fluid. So if your propeller needs a certain amount of torque, the pressure is what does that. So you have to do a flow and pressure calculation for the motors for each of these conditions. And you have to do a flow and pressure calculation for the pumps to be sure that the pumps can supply enough flow and enough pressure to get the motors to do what you want them to do. Then you have to reference your results against the specifications from Parker-Hannifin to be sure that you're not asking the pump and you're not asking the motors to do something from a pressure or flow viewpoint that they can't do. And I chose Parker-Hannifin. I think they're nice equipment and nice, I think, good reputation, but it's just a bent axis hydraulic pump and a bent axis hydraulic motor. So I think you could pick whichever one you want to pick. One of the issues that needs to be addressed is modulating subtle changes in the RPM of these propellers so you have a stable hover. And we're not talking about this in this calculation series. This is just to show that it really could fly up into the air and fly away in horizontal flight. The modulation to maintain a stable hover is a separate lecture. And I should mention from a safety point, these hydraulic pumps and motors are configured where they can have their seals and materials changed so that they can pump non-flammable fluid, which might be in a military setting useful. So you don't have pressurized flammable hydraulic fluids circulating in your device, although many military airplanes have that. And you do get some performance enhancements if you can use flammable hydraulic fluid. So that, I think, would be left up to the aviation safety people. I like the idea of a non-flammable water-based pumping fluid from toxicity and flammability issues, but it may be that the mechanical people are just going to say, don't do that, because it's works so much better if you use hydraulic oil. And again, I'll be going through the calculations fairly quickly. They're there on the paper for you to look at. Let me rephrase that. If you download that PDF, you'll have them on a piece of paper in your hand so you can look at it. I don't mind you taking notes. It's okay with me. But remember, you can also download that PDF, and all of the calculations are there for you to look at. All right, let's take a look at some numbers. And the first thing we have to do to get the drone up in the air is generate enough vertical thrust for it to go up into the air. And these pages we've already gone through, so we'll go to page 12. The program, we're using Java prop to tell us what the propeller will do. And Java prop allows us to put in the Reynolds number for different locations along the propeller. And the Reynolds number is calculated based on the they call it a fluid, but the fluid we're using is air, and a certain dimension, which is the chord moving at a certain number of feet per second. And we can't really get to these numbers until we know what we need the propeller to do in order to get the drone to go up in the air. And we can go to page 14, and looking at the propeller output value from Java prop at 0 airspeed, if there was a RPM of the propeller of 2425 RPM, then the thrust from the propeller would be 4.035 kilonewtons of force. And there's 6 propellers. So 4.4035 times 6 is 26.421, and 26.421 is 5,939 pounds of force. We can just show that in our force calculator. So we're looking at 26.421. 5,939 pounds. So the drone weighs 5,700 pounds. So if we have 5,939 pounds of vertical thrust, then the leftover thrust that's available is 239 pounds. So 239 pounds is the amount of thrust that's pushing the drone up into the air. And we can go back to page 12 and remember that 2425 RPM value. And this is our propeller, and here are the airfoil places that we're looking at as locations along the radius. And these are the values for the chord along the places of the radius. So we go to these areas and measure this chord, and that is the length value that we use in the Reynolds number calculation. And we have the 2425 RPM, and using math we can take the propeller sweeps out a circumference with each revolution. So if the circumference is a certain number of feet and it's sweeping that out at so many times per minute, that gets feet per minute, which gives feet per second. And so the 3 radiuses that we looked at, 2, 3, and 4, the chord was 430 millimeters. The velocity was 291 feet per second. The second one, the chord, this was the radius. Here's the second radius. The chord was 245 millimeters, and the velocity was 541 feet per second. And the final one was at the tip with a chord of 33 millimeters and a speed of 832.8 feet per second for those portions of the propeller. And we go back to page 12, and we see that a structure moving at 291 feet per second, having 430 millimeters of length with these parameters for the fluid, gives you that Reynolds number. And that's that one closest to the hub. The one in the middle gives you this Reynolds number, and the one furthest out gives you that Reynolds number. This Reynolds, even though it's going faster, it's a much smaller length. And so one of the available values that we can use is the Clark Y airfoil with a Reynolds number of 500,000. And so I picked that for all of them, and that's the propeller that we're using. And so that is page 12, and we didn't pick 2,428,000 because that's difficult. It makes the propeller a little less efficient to use 500,000 instead of the real value. And so we've already talked about page 13, which shows the propeller, and now we're going to go to page 14, and this shows us the thrust value for the propeller at the RPM we're talking about, at the airspeed we're talking about, giving us a thrust of 4.4035, and that gives us this total amount of thrust present on the drone, vertical thrust, from the propellers, an excess of 239 pounds of vertical thrust. So you can push that into the acceleration calculation program, and it gives us 239 pounds of force. Now this is mass, pounds, but this is calculating inside of this weight in pounds equal to mass, to give an acceleration of 1.35 feet per second squared. So it will accelerate the drone upward at 1.35 feet per second squared. And as an example, if we allowed it to do this for 20 seconds, the drone would be traveling upward at 27 feet per second, which is about 30 miles an hour straight up, having traveled a distance of 270 feet. If we put this acceleration on the drone for that amount of time. However, if we go all the way, we're on page 14, but if we go all the way to page 21, we see here a copy of the manual from the DHC-2 plane with a climbing rate in feet per minute of 1,020 feet per minute climbing rate. And so 1,020 feet per minute So 1,020 feet per minute is 17 feet per second. So I thought we may want to be a little bit conservative here and leave our maximum upward velocity at 17 feet per second. So in other words, if you keep accelerating it, it'll go faster than 17 feet per second. But if we decided we don't want to do that, we're going to put this acceleration on it until it comes to 17 feet per second. And that will take 107 feet of vertical travel and that will happen over 12.6 seconds. So 12.6 seconds later, after it starts, it'll be traveling at 17 feet per second, and it will be 107 feet in the air. So just remember that. And we'll go back to page 14 and just make a mental note that we're not going to let it go under this acceleration for 20 seconds because it'll be going too fast. And that leads us to page 15, where we just wanted to, okay, so remember, here's how the drone works, all right? This is not the CTS 800 engine, but it's the same principle. The turboshaft jet engine turning shaft output comes out of the jet engine and turns the gear, and that gear turns the pump. And the pump makes pressurized fluid that comes out of the pump. It goes through this regulatory valve up into the motor, and it spins the motor around, and it comes out of the motor and goes back through this return regulatory valve back to the pump. So that's the cycle. And this linear actuator is the device that controls how much these valves are open. And in order for there not to be overpressure catastrophes, because we keep changing the flow rate over here, we added a spring ball based emergency bypass loop where if it really exceeds the pressure by too much, it pushes this ball down and compresses this spring, and the output of the pumping system is just connected to the input of the pumping system. And the other thing that we put in there is an adjustable pressure bypass, and you'll see that this a brass or copper stem is occluding this opening, but as this is lowered down, it lets the pressurized fluid flow from the high pressure side to the low pressure side. So, and that bypass system is controlled by this servo motor controlled linear actuator. So we have control of the bypass with an emergency control so that we don't get an overpressure, and that lets us have the ability to modulate the fluid that's flowing to the propeller. And I have over here, this is one of the little drones with the Allison 250 C40. It's about 400 horsepower turboshaft jet engine. You can see that that turboshaft is turning a gear, and it's turning 3 pumps. And we'll get into what the pumps are all about. The basic point of it is you need to be able to bring pumps in and bring pumps out, because you may need more flow as you go up in altitude. And these controllers, I'll go over all this in another video. These controllers are regulating whether the output of the pump is just bypassed back to the pump, or whether the output of the pump is going down here to this manifold that's going out to the motors. And this is the little baby drone. It's not the DHC-2, but it's the same principle. And up here, we just wanted to go over the weight related issues associated with this new concept. And what we did is, remember, from a safety viewpoint, we put all this equipment on an airplane so that if there's a catastrophic loss of power, if they have enough altitude, they can initiate a glide and just do a gliding type landing, an airplane landing, which that DHC-2 is designed and has spent many, many years landing in unimproved runways. But in addition, if you already have some horizontal velocity, then a catastrophic loss of power can occur at a lower altitude because you already got your horizontal velocity. And so that's why it's on an airplane. And what we did is we took the Pratt & Whitney Wasp R985 radial engine out of the plane 290 kilograms. And we took the Hamilton standard 8-foot diameter propeller out of the plane. So those have been removed from the plane. And we put in the 6 Parker Hannifin bent axis hydraulic F12 125 motors to run the propellers. 33 times 6, 198 kilograms. We put in the Parker Hannifin F12 125 acting as a pump, 2 of those, 66 kilograms. The Parker Hannifin F12 90 pump, 2 of those, 25.7 kilograms. And the Parker Hannifin VP1-128. This is a variable output pump. This will become important for fixed wing horizontal flying, because since it's a variable output pump, we can alter how fast the propellers are spinning without changing the RPM of the jet. That's important. And so got 2 of those. We put the carbon fiber propellers. It was a little difficult to come up with a weight for those propellers. I put them at 36 or 40 pounds, 18 kilograms, 6 of those. And we added the Rolls-Royce CTS 800 jet, 2 of those. So the total added VTOL components was 846 kilograms, which is 1,865 pounds. And we removed from it 349 kilograms or 768 pounds. And so 1,865 pounds of added weight minus 768 pounds of subtracted weight. Let's see, 1,865 minus is basically 1,100 pounds. So the creation of the VTOL capability in the de Havilland DHC-2 airplane added 1,100 pounds to the weight of the plane. And so another way of looking at these values is the original plane weighed 3,000 pounds. We removed 768 pounds, so now it weighs 2,232 pounds. And then we added 1,865 pounds to it, so it would have VTOL capability, making the weight of the plane 4,097 pounds. So it went from 3,000 to 4,097. The allowed takeoff weight from the drone from all sources is 5,700 pounds. So we take the 5,700 pounds that we're allowed to have minus the 4,097 pounds of weight that's there. That leaves us 1,603 pounds of payload. And the payload consists of a fuel payload plus a non-fuel payload. And the non-fuel payload consists of human beings and items that are not human beings. So if we had 600 pounds of fuel, then we have 1,000 pounds of non-fuel payload. If we put 2 people on there at 200 pounds each, that's 400 pounds. We would have 600 pounds of payload that we can go up in the air with. And if the drone was going to fly autonomous, it could take off with 1,600 pounds of fuel. And if it was just one person flying it because they were carrying a load of this or that somewhere, then one person weighs 200 pounds and you could have 1,200 pounds of fuel. Or if the mission requires perhaps someone to keep up with all this stuff that's being transported, you have a pilot and a mission specialist, then they can transport 600 pounds of whatever they want to carry. And 600 pounds of available transport includes that they can carry 2 or maybe 3 people. So this could be a medical evacuation drone. And we'll look at page 16, which is just showing off this engine, the CTS 800. And what I did was I took images of the CTS 800 jet engine and superimposed on it my SketchUp drawing, so that when you're looking at my SketchUp drawing of this engine, that's why it looks like that. And the Parker-Hannifin bent axis pumps and motors, they look exactly the same. They're either configured as a pump or they're configured as a motor. But I duplicated them in my SketchUp program. And the reason why I did that was so that when I'm drawing out structures to scale, these pumps and motors are drawn at the size that they really are with respect to the internal scale of the whole structure. And the other thing is some dimensional data on the CTS 800. This is where I got dimensions from to make this drawing over here. And there's also some horsepower values and specific SFC standard fuel consumption values, pounds of fuel burned up per horsepower per hour, and just some details. That's page 16. Page 17 is where I wanted to just show the drone, which I've already shown you. So now we're back to page 18, and page 18 begins our place where we do these calculations. And for whatever it is that we're doing, we have a set of calculations for the motor and a set of calculations for the pump. And the calculations for the motor includes flow and pressure. And the calculations for the pump includes flow and pressure for each pump. And what we need to do, okay, and these are some, this is from the Parker-Hannifin website. These are just equations for working with pumps and motors. And I did include these efficiency calculations. That's why if you did this in a regular program, you'd say, this isn't coming out right. And the reason that it won't come out right when you do it that way is you need to put in efficiency values. And so that's why you might see that some of these values for what I'm getting are slightly different from what you're getting from a pure calculation program, because it's not fair not to put in your efficiency calculation. So I had a little trouble getting delta P to show, so I just used P as pressure. They, I think, use they use delta P for pressure, and they use big P for power. But I decided to do PWR for power and P for pressure. So the calculation for flow is the displacement of the motor times the RPM of the motor divided by 1,000 times 0.9. That's that efficiency calculation. And so we're going to have 272.8 liters per minute of fluid flowing through one motor when it's running at 2,425 RPM. 6 motors is just 6 times this. So 1,637 liters per minute is what we need to be flowing through those 6 motors to get this RPM. The torque comes from the propeller calculation page, and the torque needed was 673.9 Newton meters. And you can see we've gone back to page 14 at 0 airspeed, 2,425 RPM, 4.4035 kilonewtons, requiring, this is kilonewton meters, so 673.9 Newton meters of torque. That's page 14. That's where that came from. And the system has 3 pumps. We're going to get into that. You need extra flow when you get higher altitude because the air is thinner and you have to spin the propellers faster. In addition, we like to have that variable output pump so that we can modulate how fast the drone is flying when it's in its cruising mode. You remember, okay, and so now that we have that 673.9 Newton meters of required torque, you can run that backwards through this program and wind up figuring out how much pressure you need. And so we're done with the motor. 2 engines, we needed 1,637 liters per minute for all 6 propellers. So that divided by 2 is 818.5 liters per minute for each engine. The 2 pumps it's running, one of the pumps it's running is the F12-125. It can only go at 4,200 RPM. It can't go faster than that. So that gives us 472 liters per minute. So we need the 818.5 minus the 472. We need to get 346.5 liters per minute to that motor somehow. And since the output of the CTS 800 engine is 6,402 RPM, so we have to gear it down. That gets it from 6,402 RPM to 4,200. The flow of the pump is the displacement of the pump times the RPM of the pump. That's an efficiency value divided by 1,472 liters per minute. The torque for this pump is the displacement of the pump times the pressure divided by 63 times this efficiency, which gives 883.1 Newton meters at the pump. But remember, the jet has been geared down. So the pump needs 831.8, but the jet only needs to put out all right, I have a mistake here. What we needed at the pump was 831.8 Newton meters. The jet is geared down, so it should be 4,200 divided by 6,402 times 831.8. Shouldn't be 904, should be 831.8. But that does actually equal 545.6. So the jet itself is putting out 545.6 Newton meters to run this F12-125 pump. The Newton meters for the jet is 1,373. That's its maximum running output at full output. So we have left over 827.4 Newton meters available for us to use. If we took the F1290 pump, it can only run at 4,600 RPM. So it's the second pump. And if we run it at 4,140 RPM, it gives us the 346.5 liters per minute, which is what we needed up here. And the pump torque on the F1290 is the displacement times the pressure over this. This makes the units correct. And that gives 619 Newton meters at the pump. But again, the jet engine will be putting out the 4,140 RPM divided by 6,402 times 619. 400.2 Newton meters. So thus that means for the jet engine, it's putting out 545.6 for the F12-125 pump, and it's putting out 400.2 for the F12-80 pump, which means that the jet engine is putting out 945.8 Newton meters. And the effect of it doing that is you will have enough thrust to make this drone accelerate upward at 1.35 feet per second squared. And that will lead us to page 19, where we can show, okay, page 18, 945.8 Newton meters at the jet for each of the 2 jets. And it's 945.8 Newton meters at 6,402 RPM. That's the jet output. So if we go into this power calculation program, 945.8 Newton meters being supplied by a shaft turning at 6,402 RPM will give 850.36 horsepower. So each jet is putting out 850.36 horsepower. The total for the jets would be 850.36 times 2, or 1,701 horsepower. That's the amount of power that will give us an upward acceleration on this drone at 1.35 feet per second squared. And these are some values for the specific fuel consumption. And it's showing that it's basically 0.46 pounds of fuel per horsepower per hour. So We're using 1,701 horsepower from the two jet engines times 0.46 pounds of fuel per horsepower per hour is 783 pounds of fuel per hour. But if we divide 783 by 3,600 seconds, this is the number of seconds in an hour. It comes to 0.217 pounds of fuel per second. So if we use up 0.21 pounds of fuel per second, the drone will go up in the air at an acceleration of 1.35 feet per second squared. All right, and that's a pretty good place to be at. At least we have pounds of fuel that we're using up when we're accelerating the drone up into the air. And we can go to page 20. And we do have a conversation about the drone changing itself from just flying straight up in changing it so it's flying along. But since we were talking about fuel consumption, I wanted to talk for a moment about fuel consumption from all of the different issues. And one of the issues of fuel consumption is, what is the fuel consumption when it's just flying along at its efficient flying fixed wing horizontal airspeed of 125 miles an hour? And I'll go to page 22 and show you where this came from. But it takes 147.72 horsepower to do that. And that is using two propellers to push it along. 295.4 horsepower total. 295 horsepower times 0.46 pounds of fuel per horsepower per hour is 136 pounds of fuel per hour. That means to fly along at 125 miles an hour, it will need 136 pounds of fuel per hour to do that. If the fuel takeoff load is 600 pounds and a safety margin time, let's just say let it fly for 3 hours, then it's 3 hours of flying times 136 pounds of fuel per hour is 408 pounds of fuel, leaving over 200 pounds of fuel safety, giving us a flying range of 125, 124 miles per hour times 3 hours of 372 miles. So the plane, once it gets up in the air, has a flying range of 372 miles if it's going somewhere where it can refuel. And if it's going somewhere where it can't refuel, then it's going there and coming back range becomes 372 miles, becomes 186 miles. So it can fly somewhere for 186 miles, land, take off and come back. Or if it's going somewhere that has fuel, it can take off and fly for 372 miles and land, refuel, and come back. So now we'll go to page 22. And the economic true cruising speed is 125 miles per hour, requiring 240 horsepower to do that. I don't have the lift drag values for the plane, so I can't do a totally perfect result for the propeller. It's been a very big surprise to me. Nobody publishes lift versus drag values for airplanes. I don't know why they don't, but they don't. My intuition is the reason they don't do it is because Google has discovered that nobody cares about that. And so they don't put it out there. But anyway, this is with a single propeller plane. But we're going to use two of our propellers, the two front propellers, to provide the horizontal thrust to move it along at 125 miles an hour. So I think that means we're going to need 120 horsepower per propeller. And 120 horsepower is 89 kilowatts. 125 miles per hour is 55.8 meters per second. I decided to use 55.21 meters per second because 55.21 is in the Java prop output. So that's airspeed. That's the RPM of the propeller. It's using up or putting out 89 kilowatts of energy. It has an output thrust of 1.2135 kilonewtons and is using 333.56 newton meters of torque. And that's what we need right there, 336.5 newton meters of torque and 2548 RPM. So the F12-125 motor running at 2548 RPM needs 287 liters per minute of flow per motor, and using that displacement motor, it requires 187 bar to give it the 333.56 newton meters. And we're going to use the variable output pump if we possibly can for horizontal normal cruising flying, because if we want to speed up, the pump can do it. If we want to slow down, the pump can do it without changing the RPM of the jet. So you can flip the equations around because we know what flow we need and we know the displacement of the pump and the efficiency value, and so that gives us 2492 RPM for this pump. The M is related to the pressure and the displacement, so it's 422.1 newton meters for the pump. Remember, the jet is going to be geared down because we only want that pump to be turning at 2492. So the torque at the jet is 2492 RPM for the pump divided by 6402 RPM for the jet times the newton meters at the pump, which is 164.3 newton meters of torque at the jet level. And we have two jets doing that. So you can see if each of the jets is putting out 164.3 newton meters of torque, the two of them are putting out 328.6 newton meters of torque. And if you get this calculator and take 328.6 newton meters of torque being put out at 6,402 RPM, you get 295.44 horsepower being put out. So that's the horsepower that you need to fly along in level flight. And we'll go back to page 20. And that's where that 295 horsepower came from. That was one of the jets. Two is this. And so this shows you how we got the fuel consumption for flying along in level flight at its most efficient flying condition for horizontal flying to maximize distance traveled with respect to airspeed and fuel consumption. All right, and we were talking about flying the plane at its most efficient flying speed, because that's important. That's something we need to talk about, and it got included here on page 20 because we were talking about fuel use. But we need to go back to the topic of getting the drone to go up in the air. So it was sitting on the ground. What we wanted to do was go up in the air, and then we want it to start flying horizontally. So the first thing we look at is from the Java prop, we have 4.4035 newton meter or kilonewtons of force, and we have that from 6 propellers. So that gives us 26.421 kilonewtons of force, which is 5939 pounds, and the drone weighs 5,700 pounds. So we have 239 pounds of vertical thrust in excess of the weight of the drone. From the acceleration calculator, again, this is taking the weight of the drone, which is related to gravity, and turning it into the mass. This is done inside of it. But if you have 239 pounds of excess vertical force pushing up on the drone, and it weighs 5,700 pounds, then it will move up at 1.35 feet per second squared. It will accelerate. It will just keep going faster and faster and faster because your force is in excess of the weight of the drone. And we'll move on to page 21. And this includes the manual from the de Havilland DHC-2 plane. And it says that the rate of climb is 1,020 feet per minute. And if we do our calculation, (1,020 feet per minute is 17 feet per second. So that's the rate that it flies upward at. And based on that, I decided we will have it accelerate at 1.35 feet per second squared of acceleration until it gets to 17 feet per second, at which point we will stop the acceleration. We won't go above that. And you can plug that into the uniformly accelerated motion calculator here. You start out with a velocity of 0. You want to get to a velocity of 17 feet per second. Your acceleration is 1.35 feet per second squared. So it will travel upward a distance of 107 feet, and it will travel for 12.6 seconds, at which point it will be flying at 17 feet per second. And we want to knock out that acceleration. So in essence, we want to try to get the thrust to be equal to the weight of the drone. That's not totally correct because you are raising the drone up, and in addition to that, you are overcoming drag forces because it's flying upward. But we can at least start by saying if it was flying in a complete vacuum and you got it going at 17 feet per second, then for it to stay flying at 17 feet per second, your vertical thrust only needs to be equal to the weight of the drone. And you can go into, so the weight of the drone is only 5,700 pounds, which is 23.35 kilonewtons, divided by 6 is 3.89 kilonewtons of force per propeller. And if you go in there, 3.89, here it is, 3.89, 2,280 RPM. Torque is 595.7 Newton meters. And that allows us to do a calculation of what do we need to do with these pumps to get this drone to be having a thrust of 5,700 pounds instead of 5,939 pounds. And the F12 125 motor it is going at 2280 RPM. So this allows us to get a flow, which is 257 liters per minute, times 6 is 1,542 liters per minute, 2 jets. So we need 771 liters per minute to be created by each jet. The pressure is related to the torque and the displacement of the motor, and that gives us a needed pressure of 333.6 bar. I keep calling this the VP1 128. It's actually the VP1 130. The displacement is 128, but the Parker-Hannifin name for it is VP1 130. Its maximum delta P is 350 bar, so we're okay. The first pump we have running at 4,200 RPM. And if you take the 4,200 RPM, because that's as fast as it can go, you can go look it up on the Parker-Hannifin specification sheets. So 4,200 RPM times this displacement times the adjustment factors comes out that this number one pump is going to make 472 liters per minute. We need 771, so 771 minus 472 is 299. So we need 299 liters per minute to be given to us by something else. And that's the VPN VP1-128 variable output pump. The F12-125 pump that's creating this flow at this pressure needs 735.4 Newton meters of torque at the pump, but remember it's geared down because it can't go any faster than 4,200 RPM. So the torque on the jet is equal to the torque on the pump times this gearing down factor, and means that the jet will be looking at 483 Newton meters. The F1290 pump is in the system, but it's not being used. It's on bypass, and we're going to switch to the VP1-128 pump to help us to keep the upward flying speed at 17 feet per second. So it's not accelerating, it's just 17 feet per second. And that takes us to page 22. And page 22 was the page where I just decided to talk about the getting the drone up to its normal, standard, most efficient flying speed. So we're going to skip right over it. We've already talked about page 22, and we're going to move on because we're talking about, this is stable horizontal flying. We're talking about getting the drone up into the air, the transition. So we'll go to page 23, and this 128 VP1-130 pump, its displacement is 128. We can rearrange terms and find that we want it to be turning at 2595 RPM. Maximum RPM for it is 3000, so we're okay. The torque for this pump is the displacement times the pressure plus the adjustment factors to get the units correct. And so the torque for the pump at the pump is 735.4 Newton meters, but the torque at the jet is the torque at the pump times the conversion factor. So the jet is seeing 306 Newton meters of torque that it needs to create for this pump. And so the total Newton meters of torque seen by the jet for each of the jets is 483 from the F12-125 pump and 306 from the VP1-128 pump. So the jet is seeing 789 Newton meters of torque. And you can put that into this technology calculator, and 789 Newton meters at 6,402 RPM is 709.38 horsepower. So in order for it to fly upwards at 17 feet per second, it needs 709.38 horsepower per jet. Times 2 is 1,419, and once again we do the 1,419 horsepower times 0.46 pounds of fuel per hour per horsepower is 653 pounds per hour, but you divide that by 3,600 seconds per hour to give you a requirement of 0.18 pounds of fuel per second during the seconds that it's traveling upward at 17 feet per second. And so the fuel calculation, you'll notice we have to do a flow calculation, a pressure calculation for the motor, and a flow calculation and a pressure calculation for the pumps, and a flow calculation and a torque and a RPM calculation for the jet. And then we have to do a calculation to get fuel flow. It's not a big deal, but it's just that all of these factors need to be considered if you're going to say this is feasible. And so that's what we're doing. So we went from 0 feet per second to 17 feet per second. It took 12.6 seconds. The drone will be 107 feet in the air. We will then stop the acceleration and maintain that 17 feet per second for another 25 seconds. And here is why it's 25 seconds. It's 25 seconds because I just picked 25 seconds myself. I made a decision that will put it up in the air another 425 feet. I think the drone, before it tries to transition to horizontal flying, should have enough vertical distance up in the air that reactions can be made by the pilot if that transition doesn't go exactly the way you wanted it to go. And so if you're 400 feet in the air, you have some distance to try to overcome a problem if there's a problem. Hopefully there won't be a problem. But that's where 425 feet came from. It came from the fact that it was 25 seconds of flying at 17 feet per second. And the reason why it was 25 seconds is because I picked that. And the going from 0 feet per second to 17 feet per second requires 850.3 horsepower times 0.46 pounds of fuel per hour divided by the seconds is 0.21 pounds of fuel per second for the 12 seconds. And then the steady upward flying vertically at 17 feet per second, not accelerating, requires 709 horsepower, less than what it takes to accelerate it for 2 jets. And that is 0.18 pounds of fuel use per second. So 0 altitude, 0 velocity to 107 feet in the air and an acceleration of 17 feet per second takes 12 seconds. And then we fly at 17 feet per second for 25 more seconds. We get a total altitude in the air of 532 feet, and this will take us 37.6 seconds to get to 532 feet. The use of fuel will be 0.217 pounds of fuel per second times 12 seconds plus 0.18 pounds of fuel per second times 25 seconds, which is 7.23. Yeah, there it is, 7.2. So the drone, it has 1,000 pounds of payload, 600 pounds of fuel, will take off, go straight up for 37 seconds. It will use up 7.23 pounds of fuel, and it will be 532 feet in the air. And so that's the vertical portion of the discussion. All right, we're on page 23. We've got the drone up in the air. It's time to get it flying horizontally. And you can see that it takes time to explain all this. I could talk faster and actually leave stuff out, but I really wanted to discuss it and describe it in a way where it's exceptionally clear what's going on, so that people who, again, have the opinion this is a great drone and a great plan and ought to be created, but it's just impossible, I can say, well, look at the math. The math doesn't say that it's impossible. And so it just takes a while to say all of it. So let's move on to page 24. And that involves a little bit of lecturing. The rotors tilt, so you can have 100% vertical thrust or 100% horizontal thrust, or you can tilt them and have a component of horizontal thrust and a component of vertical thrust. The horizontal thrust will tend to make the drone start flying horizontally. As the drone begins to start flying, it has wings, and the wings will begin to generate lift. The stall speed of the drone is 60 miles per hour. So once it's going 60 miles per hour, the lift from the wings is equal to the weight of the drone. So the lift related to the wings, just from aerodynamics, is related to the square of the speed. And so, for example, if all of the weight of the plane is created by the wings flying at 60 miles per hour, how fast does the plane need to be flying so that half of the weight of the drone is supported by the wings? And you do that with these values squared equations, and then you take the square root of what's left over. And anyway, what it says is, if the drone is going at 40 miles per hour, then the lift from the wings will be 1/2 of the weight of the drone. And you can do the same square root activity again to say, all right, fine, well, let's do 1/2 of that, which would be 1/4 of the weight of the drone. And 1/4 of the weight of the drone If you have half of the weight of the drone held up by the wings at 40 miles per hour, then a quarter of the weight of the drone will be held up by the wings. Comes out to 28. I'm just going to use 30 miles per hour. And remember, the drone weighs 5,700 pounds, and you have half of the weight of the drone, which is 20, I can't do that in my head, 2,800 pounds. If 2,800 pounds of the drone is being held up by the wings, then you can take that whole 2,800 pounds if you want to and convert it into horizontal thrust. And that is how you get the drone flying in a short amount of time to the airspeed you want. And we'll go on to page 25. And unfortunately, from a lecture viewpoint, it's just complicated. We have to talk about the horizontal condition of the plane and the vertical condition of the plane. We're going to take vertical thrust away from the plane and turn it into horizontal thrust. If you take enough vertical thrust away from the plane that you don't have a vertical thrust equal to the weight of the plane, then the plane is going to start going down towards the ground. It won't be going down at 32 feet per second squared, the force of gravity, unless you take away all of the lift. So that's another thing to remember. I divided it into a set of steps. We'll go from 0 miles per hour of airspeed to 30 miles per hour of airspeed. Then we'll go from 30 miles of airspeed to 40 miles per hour of airspeed. And then we'll go from 40 miles per hour of airspeed to 60 miles per hour of airspeed. The two jet engines remain at their full power the whole time. So the total thrust available from the 6 propellers is 5,939 pounds. This will be divided between vertical thrust and horizontal thrust. We've already got the plane up at 523 feet in the air. If we change the vertical thrust so that it's 5,415 pounds, then the downforce on the drone is 285 pounds. And that's because 5,415 is 285 pounds less than the weight of the drone. So we have a 285 pound force pushing down on the drone. That's the vertical component. We had 239 pounds of force, vertical force, extra, and we added another 285 pounds. So the force horizontally pushing on the drone is 524 pounds. So 524 pounds of force horizontally pushing on this drone at 5,700 pounds accelerates the drone in a horizontal direction 2.96 feet per second squared. Okay, so we want to take this acceleration and get to 30 miles per hour. So if we start at 0 miles per hour of horizontal speed and we want to go to 30 miles per hour of horizontal speed, and we have 2.96 feet per second squared of acceleration, then the drone will travel horizontally 327 feet, and it will take 14.9 seconds to get it to 30 miles per hour. The downforce on the drone is 285 pounds, and with this mass, the downward acceleration of the drone is 1.61 feet per second squared. So this is horizontal. That's vertical. We'll go to page 26. At this point, everything starts to get complicated because it was traveling up at 17 feet per second when it reached this altitude. It took 14.9 seconds to get it up to 30 miles per hour. It had a minus 1.61 feet per second negative acceleration on it because we took away 285 pounds of vertical thrust. It took 14.9 seconds to go to 30 miles per hour. So if we were going up at 17 feet per second and we put a minus 1.61 feet per second vertical force acceleration on the drone for 14.9 seconds, I thought this meant the drone would go down by 74.6 feet, but I'm not sure that's true. It could be that it will go up by 74.6 feet because If it's traveling 17 feet per second times 10 seconds is 170 feet times 5 seconds is another 80. So 170 is 250 feet. So it should have gone in 14 seconds. It should have gone up 250 feet, but it didn't. But that's because you have this negative vertical acceleration on it. So I'm beginning to think it actually went from 532 feet in the air up. But the truth is, it doesn't matter if it went up 74 feet or down 74 feet. It doesn't matter because you're 500 feet in the air. But you also obtained an airspeed, a horizontal airspeed of 30 miles per hour, and that means 1/4 of the weight of the drone is being held up by the wings. And so 3/4 of the weight of the drone needs to be held up by the vertical force, and that is 4,275 pounds. So to get an understanding of the vertical thrust from the propellers, you have to factor in that they are traveling, they're not at zero airspeed, and you have to go back to Java prop and add in the 30 miles per hour of airspeed that you have. Don't change the torque, and the thrust goes down because of the airspeed, and the total thrust is this times 6 propellers is that, which is 5,294 pounds. So that's how much thrust you have available. Now, remember we took 285 pounds of vertical thrust away from the drone. So to get it from 0 miles per hour of horizontal airspeed to 30 miles per hour of horizontal airspeed. So now let's just put it back because we have it available. So the downward weight of the drone is 4,275 pounds because of the lift from the wings. So the upward thrust on the drone is 4,275 pounds plus 285 pounds is 4,560 pounds. So that's the vertical thrust we want to put on the drone. Our propellers are giving us 5,294 pounds. So 5,294 pounds of available thrust minus 4,560 pounds of thrust that is reserved to be vertical thrust remains 734 pounds of horizontal thrust. So it takes less time because we're not going from 0 to 30 miles per hour. We're going from 30 to 40 miles per hour. That's not that much. So our force of 734 pounds of thrust against this mass will give us an acceleration of 4.14 feet per second. And if we started at 30 miles per hour and we want to go to 40 miles per hour and we have 4.14 feet per second squared of acceleration, horizontal acceleration, it will travel for 182 feet, and in 3.54 seconds it will now be going at 40 miles per hour. And so let's see what that comes to. So I have during the time, okay, so and it went so going from 0 to 30, it traveled horizontally 327 feet. That's page 25. And now, going from 30 to 40, it traveled another 182 feet. And I'm just not sure. It doesn't much matter. Let's say that it dropped down 74 feet and it has a vertical downward velocity of 6.99 feet per second, because we are have been giving the drone a minus 1.61 feet per second squared negative acceleration on it for 14.9 seconds. So that means that it's traveling, because of that, it's traveling down at 6.99 feet per second. So now we'll go to page 27. And again, this is just one more way of saying what's going on, because we're paying attention to two separate problems at the same time, vertical and horizontal. We went from 30 to 40 miles per hour Vertical status of the drone is it went down by 74 feet and it had a negative velocity of 6.99 feet per second, although this might be that it went up by 74 feet. The tilt rotors were adjusted at 30 miles per hour to give a down-directed weight on the drone of 285 pounds. But once it got up to 30 miles per hour, we switched around how we're adjusting the thrust so that we have a net upward thrust now on the drone of 285 pounds. This gives it an upward acceleration of 1.61 feet per second squared. And so while we were going from an airspeed of 30 miles per hour to an airspeed of 40 miles per hour, the drone went vertically down by 14.7 feet because this is how fast it was going down. This is how many seconds went by, and this was our acceleration on the drone. And it altered its condition so that it's now going down at 1.29 feet per second. And it traveled down like that for 14.7 feet. And now it's going 40 miles per hour. And when it's going 40 miles per hour, 1/2 of the weight of the drone is supported by the wings. So the downward weight of the drone is now only 2,850 pounds because the wings are holding up half the weight of the drone. So this means, again, and remember, we got to look at 40 miles per hour to get the right thrust output from the propellers. 17.8 meters per second is 40 miles per hour, and you go down here to 17, right around in here. 3.76 kilonewtons times 6 propellers is 22.56. So there's 5,071 pounds of thrust is available from the propellers. These are adjusted so that the upward vertical thrust applied to the drone is equal to its downward directed weight, which is not 5,700 pounds because the wings are holding up half of its weight. Its downward directed weight is 2,850 pounds, and we again added 285 pounds of additional upward force on the drone. So that means we have the weight of the drone, 2,850 pounds, plus the 285 extra that we added, so the vertical thrust is 3,135 pounds. But the thrust available from the propellers is 5,071 pounds. So 5,071 pounds minus 3,135 pounds. So this is 5,071 pounds of available thrust. This is 3,135 pounds that we are using as vertical thrust. This means that 5,071 pounds of available thrust minus 3,135 pounds of thrust that we are reserving as vertical gives us 1,936 pounds of thrust that can be used as horizontal force. And that's going to really get this drone going. And we'll go down a little bit. Whoops, I'm sorry here. We'll go down a little bit more. And you can see so we had 1,936 pounds of thrust available as horizontal force. And if you put 1,936 pounds of force on a 5,700 pound mass equivalent, you'll get an acceleration of 10.9 feet per second squared. So that's how fast that amount of horizontal thrust is going to accelerate the drone. 10.9 feet per second. And so now we can go to page 28. And here we did something that is called slipstreaming, which is I added something to this document that I didn't tell you about because I left out the page of going from 40 miles per hour to 60 miles per hour. So that's been fixed. That page has been added. I put it on my website. So if you downloaded the PDF from my website, if you will just throw that away and download it again, it will have page 29 because page 29, it really should be page 28 and page 28 should be page, but I'm not going to change all that. Page 28 is the conclusion page, but let's go to page 29. And this is what it shows us. remember we had 10.9 feet per second of acceleration, feet per second squared of acceleration. We want to go from 40 miles per hour to 60 miles per hour. That will take 197 feet, and the time for that will be 2.69 seconds. So in a time span of 2.69 seconds, it will travel 197 feet, and it will now be going at 60 miles per hour. It had an upward directed acceleration of 1.61 feet per second squared. So if you put that 1.61 feet per second squared of upward acceleration on it for this time interval of 2.69 seconds, it goes up in the air by 2 feet. Translation, not much happened. But what has happened is going from 0 to 30 miles per hour, maybe it went down 74 feet. Going from 30 to 40, it went down 14 feet. And then going from 40 to 60, it went up by 2 feet. But what that means is, okay, you're still way up in the air and you're not close to the ground. And you are now going at 60 miles per hour. And at 60 miles per hour, the weight of the drone is supported by the wings. And the end result of all of this is it went down by 85 feet. It traveled, this is 0 to 30 miles per hour, this is 30 to 40 miles per hour, and this is 40 to 60 miles per hour. So it went horizontally 706 feet, dropped down 85 feet. It took 14 seconds for 0 to 30, 3 seconds from 30 to 40, and 2 seconds from 40 to 60. So it took 21 seconds. Once it got up in the air, 21 seconds later, it was at 60 miles per hour. It was on normal full jet engine power for all of this with an output of 850.36 horsepower. So that's a total for the two jets of 17 and 1 horsepower times 0.46 pounds of fuel per horsepower divided by 3,600 to give 0.21 pounds of fuel per second. So the end result is, in 21 seconds, it used up 4 pounds of fuel and is now going horizontally at 60 miles per hour. So now, slipstreaming. Here's page 30. I know you're probably saying, whoa, what is page 30? So let's go look at page 30 and I'll get back to it. One of the questions I had was, can it fly at 143 miles per hour? Does this setup allow that? That was one question. I'm sure you saw page 31. Remember when we were at Gunnison and flying around and having fun, the pilots were going along the valley like they're supposed to, listening to their scientists who told them they had some time off to practice, and they immediately went up to the top of the mountain and landed up there on what I called the crow's nest, which is 12,000 feet. And I got nervous and said, can that drone get to 12,000 feet? So that's what this page is. But we're not going to do these 2 pages yet. I just wanted you, and that's slipstreaming. So page 31, page 30, and page 29 are at my website. You can get them. We'll go back to page 28 and we'll finish the discussion that started all this. Vertically, we went from 0 altitude up in the air over a span of 37 seconds. We used 4.5 pounds of fuel and we were 532 feet in the air. Then we began our transition to horizontal flying. We traveled 706 feet horizontally over a span of 21 seconds and used up 4 pounds of fuel. So it took 4.5 pounds of fuel to get up in the air. It took 4.44 pounds of fuel to get up to 60 miles per hour of airspeed. So, thus, conclusion, the de Havilland DHC-2 weighing 3,000 pounds with 1,100 pounds of additional VTOL parts plus 600 pounds of fuel and 1,000 pounds of non-fuel payload sitting on the ground, 0 altitude, 0 horizontal airspeed, It changed its status to being 437 feet in the air, flying along at 60 miles per hour. It is now in stable horizontal flight. And the entire process took 8.94 pounds of fuel, and it took 58 seconds for it to do that. And my opinion is that is not bad. And I wish I knew. But I think if you went to many military pilots and said, hey, look, would you like to take four to 6 weeks off, go to class for a week and a half, go to the simulator for a week and a half, and then go fly this plane? Because this plane is not a plane that you have ever seen before. You don't need a runway. You land it wherever you feel like, and then you take off, get it up in the air, and fly away with it. And it flies like an airplane. And, you know, you're flying along and see someplace, a road or a parking lot. I mean, you know, you can't violate flying rules. But basically, if you see a place you want to land, you just land. And when you're done with whatever you're doing there, you just take off. Oh, well, hey, look, we'll see. Here's Korea. Let's minimize this. If you could ever get the Koreans to agree to it, would the pilot say, yeah, I'll take off, I'll go out here, and I'll put it down right there. And I'll wave to these people here who are looking at us with a very shocked look on their face, and we'll walk over here and shake their hands, and we'll walk back to the plane. We'll plane straight up in the air, fly around down here, and land it on the ground. And would those pilots do that? It seems to me like they would. Okay, so we'll do very quickly, we'll go back to reality here, which is page 29, which was going from 40 miles per hour to 60 miles per hour. And now we need to go to page 30, which is if you go back to the manual, the maximum flying speed recommended for a fully loaded drone is 143 miles per hour. And this was with its weight of 5,100 pounds. But Viking, who now owns and manages the DHC-2, got it where it's got a flying weight, all up weight, AUW of 6,000 pounds. And we're only putting an AUW of 5,700 pounds. It lists 300 horsepower for it to fly at 103 miles per hour. And so we'll split that between two propellers at 150 horsepower. I don't have lift versus drag. So all I can say is if 300 horsepower did it, then I'll create 150 horsepower from each propeller, and that's 112 kilowatts, and you can, and at 143 miles per hour is 63 meters per second. Java prop, if you put in, Java prop allows you to obtain an answer if you say what power do you want it to create. So we can say, I want it to create 112,000 watts. And so Java prop says, okay, RPM is 2864. Remember, you have to put in the airspeed of 63.97 meters per second because we're going 143 miles per hour. The thrust is 1.2 kilonewton and the torque is 373. And then you just go through the same exact set of calculations that you did before. This is the flow, 2864 times the displacement, and then you multiply. We only have two propellers. Okay, remember, we only have two propellers. So at 398 liters per minute per propeller, the pressure needed is the torque times the displacement. We'll use, which pumps are we going to use? And I think what I came down to is you have to use all three pumps. But the first pump is the F1290. The second pump is the VP1 128, which is really the VP1 130. And the F1290 is running at 4140 RPM, giving an output of 346 liters per minute. The Newton meters for the F1290 pump is 343, but it's geared down, so it's 222 Newton meters at the jet. Flow needed is 398. So the VP1 supplies. Oh, I said we use all three pumps when we go to 12,000 feet. When we're just flying along at 143 miles per hour, we did 125 miles per hour just using the variable output pump. But if you want to go from 125 miles per hour up to 143 miles per hour, you have to bring on board the F1290, because this VP1 128 cannot supply enough flow to get you to 143 miles per hour. So it's two pumps, not one pump, it's not three pumps, it's two pumps. The contribution needed from the VP1 128 is 51.5 liters per minute. It's running at 3,000 RPM. So you can turn your equation around. If you know the RPM of the pump and you know the flow that you need, you can get the displacement. And that, so you adjust the swash plate of the variable output pump so that the displacement of the pump is 15.45 centimeters cubed per revolution. And then you can take that 15.45 centimeters cubed of displacement times the pressure, and that gives you the Newton meters. So the Newton meters for the VP1 128 is 27 at the jet because of this gearing down, and the Newton meters for the F1290 is 223. I'm sorry, the F1290 has 220 Newton meters at the jet, and the VP1 128 has 27 Newton meters at the jet. 222 Newton meters at 6,402 RPM is 199.6 horsepower for the F1290 pump. 27 Newton meters at 6,402 RPM is 24 horsepower for the VP1 128. If you add these two horsepowers together, you get 223.6 horsepower per jet to push the drone at 143 miles per hour. And that's 447.2 horsepower. And 447 is a lot more than the 300 that the manual said was needed, but I think that's because these propellers have been optimized for thrust at zero airspeed. So they're the fat cord, high thrust at low airspeed propellers, and as you start going faster and faster, they become less and less efficient. And so we need 400 horsepower to go, 447 horsepower to go 143 miles per hour, because our propellers are optimized for a different purpose. And 447.2 horsepower times 0.646 pounds of fuel per hour per horsepower is 205.7 pounds of fuel to fly at 143 miles per hour. So if we want to use 205.7 fuel, if we want to use 205.7 pounds of fuel per hour, we can fly at 143 miles per hour. If we would rather use 136 pounds, which is almost 70 pounds per hour less, then we need to stay at 125 miles per hour. Okay, and the final thing we're going to do here is, and I was going to go in here to go back to Gunnison, but it just takes too much time. So you can go back to I think it's the number 10, part 10 YouTube, and watch the pilots flying around in Gunnison. But they found a peak that was 12,000 feet. And the question is, can this drone, not by flying with fixed wing flying, but with drone flying, go up right there? It's 12,000 feet. So can they fly along and then take this plane and go straight up with it like this and land it at 12,000 feet? And the problem that you get into is the air becomes less dense as you go up in altitude, and the propellers are not as efficient. So we have this converter, and you put in the altitude in meters. That's 13,000 feet. I wanted them to have 1,000 feet of space just so they're, pilots. I just want them to be able to get up above that 12,000 foot point before they have to land on it. So I put in 13,000 feet. There's a temperature offset. This gives you the density of the air, 0.9121. That offset is based on this official recommendation of -6. So in Java prop, you can type in the options, you can type in an air density of 0.9121, and that tells you the output capabilities of the props. And to get full, now the Newton meters that's available, because you're using the VP1 pump, you can't go above 625 Newton meters, because that's more pressure than the VP1 pump can take. And so that limits. But it's 4.0842 kilonewtons of thrust, and it says you need 2,702 RPM. And you can take the 2,702 RPM, and this is Mach, and you can look at the Mach number, and we are less than the speed of sound, and people say 0.9 is okay. That's okay for a propeller. And one of the things that this other program allows you to do, it tells you what the speed of sound is too, also. And in the options box of Java prop, you can put in what the new value for the speed of sound is. So we're okay. And now let's see if we have enough to get that drone to go up to 12,000 feet. And a thrust of 4.082 kilonewtons is 5,508 pounds of total thrust. The pressure is 350 bar. That's where that 625 comes from. And the max pressure for the VP1 128, 130 pump is 350. So we're okay there. 3 pumps, the F12 125 at 4,200 RPM, the F12 90 at 4,140 RPM, and the VP1 128 at 3,000 RPM gives you these 3 outputs. Those 3 outputs added together is that many liters per minute per jet. And you have 2 jets, so if you double it, you have 23, 29 liters per minute from the 2 jets. Divided by 6 is 388 liters per minute per propeller. You can turn your equation around and find out that the propeller RPM that's available from this much flow is 2793, and the amount that we needed was 2702. So we're okay. And but we do have this. If we had 1,600 pounds, fuel plus non-fuel, our max thrust is 5,508 pounds, so we can't do that. We need to have 200 pounds of excess thrust in order to get the drone to be controllable. So we want them to get to 12,000 feet, and if they want to go up 10 or 12 feet, okay, we got them up here sitting on this peak, and they're looking down on the valley. They're looking down at the scientists who are saying, "What are you guys doing up there?" And they're like, we're practicing landing. And they say, "You need to get that thing in the air and come back down here. We don't want you sitting up there on that tiny little spot up there." And they're like, "Okay." And so in order for them to get off of their little landing strip, they have to give more thrust than their weight to get it to go up. And so that's why I decided you have to give them 200 pounds. So instead of 5,508, their total weight is 5,308. And so the drone weighs 4,097 pounds. So 5,308 minus 4,097 means that the fuel plus non-fuel payload is 1,211 pounds. So that's, as long as they agree not to put 1,600 pounds in that drone, they can go up there and sit on the peak. And I suppose we should go to Gunnison and just let them perch up there and be pilots. It's what they want to do anyway. And so we're on our way to, where is Montrose Airport. So we flew over, they flew over here and they just played around for an hour and a half while we drove the Humvees and the fuel tanker and the 2 tour buses, and finally got over here and set up our test station. And they took off in the airplane because we told them they could practice. And they, okay, so you can see here, okay, this is 8,094 feet, and this is 13,122 feet. So let's see what they can do up there. And I think the place where I had them, yeah, 13,206 feet. So this is where they want to land, right here. And they have, we calculated out for them that they can land here at 13,000 feet like a mighty eagle and perch up here and look around. We'll be down here with the Humvees saying, "What, you guys, what are you doing up there? You need to come back." And so they will hop in the plane. They have enough excess thrust to go up in the air, and they point the nose down, and then they can go, by drone flying, they can just go right down. I see this. So this is at 12,000 feet. So they can go up in the air here and go down there, and then they can fly along and be reasonable and tell us, you know, that we're practicing like you told us to. So now they're at 12,000 feet, and they can come on back down here like they wanted to. And all they needed to do to make that happen was not quite, and of course they used up a bunch of their, so this is all the way down to here is 8,001 feet. So we allowed them to play. And that got us to page 31. And that's the math that says to me that this drone can do this. And it just seems to me like the military would go, wow. And I don't know. I have a feeling the military pilots would say, yeah, I want to do that. That looks cool. All right, so we're done, and appreciate your interest and attention. Part 12 is coming. We're going to go back to the unified control panel and work our way through that. All right, and if you'll remember, I told you I was curious about the commanding officer in his forward operating base got this news about the soldiers in trouble, and he knew there was about 3 minutes left before the drones got there. And so this is 50 meters, 150 feet. So he took off, and either in his little truck or running down to the place where they keep the drones. And I've done an entire this is in SketchUp. I've done an entire presentation on this. I don't remember which one it was, but they have their drones in this little airfield that has been created by, again, poor Sergeant Charlie, who was put in charge of all this. And you can see this is a little hard for my drawing program, but this is one of the drones that was brought out to the takeoff area. And the commanding officer runs down in here, somewhere in here where they have set up their control room for running the drones. And and I think I'm just showing this because it's cool, but this is from Keyshot, a rendering of these drones kind of parked inside this protected, those are trusses. Above that are sandbags, not totally protected, but protected some. And he runs in here and runs through this alleyway back to the control area to watch them begin their attack upon the soldiers the enemy soldiers in that building. And I just thought I would do a little story of how I imagine that might work, where the commanding officer zips into the control room and says, "Go, you guys, really just keep doing what you're doing. I'm here to be available as the commanding officer, and also I'm here to listen and learn what's going on." And they'll say, "Well, we're close to them having visual contact with the area of interest." And so that's the story. And I think I'm going to make a separate, I guess, part 12 video where I go over that story. The drones are they're going to be flying. I got one guy in there, but there's actually one person in there, the pilot. There's another person in there that's the mission specialist, who will pick up these smart mortars one by one, and they will be launched out of the base of the plane to have their effect on the enemy forces in that building. And you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 12 of them in there. Plenty of space in here for the second mission specialist to pick one out of the rack, put it down here, and drop it. And there it goes. It's got 4.5 pounds of C4. These are the flight control surfaces. There's 2 more of these on the bottom of it. And I'm just going to tell the story. This is the tilt rotor mechanism. I'm just going to tell it. Here are these jet engines up here. I'm going to tell a little story about, and I realize I'm just making it up. I have no idea what would happen, but I can imagine how it might go. And that's our next part 12.